Hi, today's video lesson is all about the speed of sound, mostly through air, but we'll take a look at how the speed of sound travels through other materials as well. What we see in terms of how sound travels through various objects, right? It totally depends on what you're moving through, right? Sound is going to travel different through solids versus liquids versus gases. And even in those various states of matter, we're going to see differences in how it behaves through some solids, differences in liquids, and differences in gases. The general trend that we see is that sound will travel fastest through solids, then liquids, then gases being the slowest typically. Again, there are a couple that are going to kind of buck that trend a little bit, but more often than not, solids are the fastest, liquids are in the middle, gases are the slowest. And how we can determine that speed of sound, it's actually based on the elasticity of an object and the density of that medium as well. So what we see here is that the higher the elasticity is, the faster we're going to have sound travel through it. What we mean by elasticity, it stems from this term, the elastic modulus, which is about how that sound is going to travel through a rigid object versus through a flexible object. So a higher elasticity is actually going to be correlated with an object that is stiff, rigid, and doesn't change much when a force or some external pressure is applied to it. As opposed to an object with a lower elasticity, we're actually going to see that as a material that's going to be more willing to change its shape as a result of any external forces or pressures that are applied to it. Higher elasticity objects are going to be more of your metals. Think steel, aluminum, iron, lead. Think those types of materials where they tend to be much more rigid than other materials will be. So they have high elasticities, and it's based on their ability to actually not deform and not change shape. Why that high elasticity allows sound to travel faster is because when that wave enters that medium and it starts interacting with the particles throughout whatever object it's moving through, if the material doesn't change its shape, that means it's going to be more efficient for allowing that sound to travel through it. So the higher elasticity, the more rigid it is, the faster that sound will move because it's an efficient movement through. We don't lose energy to deformation. Objects that have lower densities then are going to cause sound to travel faster. And think about what that means in terms of our density. If you have a low density, that means you have less mass per volume. Having less mass per volume is going to be correlated with having a lower inertia per volume, because remember your relationship between mass and inertia, right? The higher mass objects have more inertia, harder to get them to start and stop moving. Lower mass objects have lower inertia, easier to get them to start and stop moving. So if the density of a material is lower, when that sound wave gets to those particles, if it has less mass per volume, it has less inertia, meaning that sound can get to it, make contact with the particles, and it's easier to get those particles to change what they're doing based on that density. What we then have is that relationship between elasticity and density. And solids, that high elasticity tends to overpower the higher density that they have. Because if you compare a solid to a gas, solids are going to have a higher density than a gas will. But the amount of elasticity that solid has is substantially greater than the low elasticity of the gas. So that's where we see this difference show up. Right? The substantially higher elasticity is able to counteract and basically overpower the density differences that we see, causing solids to allow sound to travel faster, then liquids, then gases. Describing how this then applies to speed of sound in air, because our ears are adjusted to hearing things based on the air that's around us. Even though sound travels faster through solids and liquids, our ears are not accustomed to hearing sounds in those different mediums. That's why when you go underwater, sound travels faster through water than it does through air, but our ears aren't used to it. We're not adapted to having that constant water pressure around our eardrums. So when sound gets to us, it gets there faster, but it's very unclear. And again, that's based on the adaptation of our ears and being surrounded by air as opposed to being surrounded by water. How we look at our formula for speed of sound in air is 331 meters per second plus 0.6 times the temperature in degrees Celsius. An increase in temperature is going to yield an increase in the speed of sound in air. So the warmer the air is, the faster sound moves. The colder the air is, the slower sound moves. And you can see in the table to the right what the different mediums are and different temperatures and how fast that sound is going to move through it. So really, air at 25 degrees Celsius, which is in the 70s for degrees Fahrenheit, is substantially slower than almost all the solids and all the liquids that are present there. Right? It's not that fast. Now, granted, 346 meters per second is still very, very, very fast. I mean, that's, you're getting close to a quarter mile if you want to put that into our standard units of measurement. It can move about a quarter mile per second. Still fast, but you look at other materials and it's not as much. Again, rationale between elasticity and density. As that temperature increases for air, the elasticity of the air is actually going to go down because the particles have more energy. Right? We're going to see that more energy is going to cause the air to be more flexible per se, so that elasticity drops. However, the density falls as well. Right? Because if you think ideal gas laws, right, you start increasing your temperature, you're going to increase that volume. So if you have a higher volume with the same amount of particles, you have a lower density. That lower density results in a lower inertia for the particles that are present, or a perceived inertia, I should say. So the elasticity drops, which would actually make it be slower, but the density drops by a greater rate, which is going to cause that temperature increase to cause the speed to increase in air as well. Other ways you could find speed of sound in air, you could certainly do delta x over delta t, right? Make a sound and time how long it takes to travel a set distance. You could certainly do that. If you know a frequency and a wavelength, or a period and a wavelength, you could find the velocity that way as well. This becomes a nice way to just be able to walk outside, measure temperature, and say, okay, here's how fast sound should be moving. Now you have a handful of ways to look at speed of sound in air, right? You can do it based on temperature, based on wave properties, and based on simple mechanics. So there's your speed of sound, right, through different materials, looking at the elasticity and the density, as well as temperature, and how they all relate to that speed traveling through a substance.